Hi, this is the lesson activity for Math 205, Lesson 4. I want to write this vector equation as a system of equations. So I'm going to distribute the x variable to the entire vector that it's being multiplied by. So I'm going to have a new vector 2x1, 3x1, 0x1 plus 7x2, 3x2, 4x2 equals 5, 0, 8. And then I can read off three separate equations component-wise. So read the first component from each vector, the second from each vector, and the third from each vector to make three equations. So I have 2x1 plus 7x2 equals 5. 3x1 plus 3x2 equals 0. And 0x1 plus 4x2 equals 8. So there's my three equations. Okay, now I'm going to go backwards. I have a system of linear equations and I want to write it as a vector equation. So I need my coefficients that are on x1 plus a vector that holds the coefficients on x2 equals a vector of constants. So my x1 coefficients are 4 and 3, x2 coefficients are -1 and 1, and my constants are 6 and 7. Okay, write a vector equation that potentially expresses 0, 2, 13 as a linear combination of 1, 2, 3, and 5, 11, 20. Okay, so a linear combination is where you put some weights on the two given vectors and add them together. And we're hoping to be able to find weights to put on 1, 2, 3, and 5, 11, 20 to build 0, 2, 13. So my vector equation is going to be 1, 2, 3 times an unknown weight x1 plus 5, 11, 20 times another unknown weight x2, and we're hoping to find an x1 and x2 that will allow this to add up to 0, 2, 13. To write this as a system of linear equations, you read component-wise. So I have x1 plus 5x2 equals 0, 2x1 plus 11x2 equals 2, and 3x1 plus 20x2 equals 13. And then to write this as an augmented system, I make a matrix where I enter my x1 coefficients in the first column. So 1, 2, 3, 5, 11, 20. Those are my x2 coefficients. And then I augment with the constants from the other side of the equal sign, 0, 2, 13. Now we want to determine whether or not 0, 2, 13 is a linear combination of 1, 2, 3, and 5, 11, 20. So I'm going to row reduce the augmented matrix that I wrote up above. Okay, so I already have a 1 in the first pivot position. So I want to eliminate the 2 and the 3 below it. So I'm going to do 2 row replacements at once here. I'm going to replace row 2 with itself plus -2 row 1. And I'm going to replace row 3 with itself plus -3 row 1. And I'm going to get a row equivalent matrix. Row 1 is not changing, so I'm just going to copy that one. And then row 2 is going to become 0, and then -2 times 5 is -10, plus 11 is 1. -2 times 0 is 0, plus 2 is 2. -3 times 1 is -3, plus 3 is 0. -3 times 5 is -15, plus 20 is 5. And then -3 times 0 is 0, plus 13 is 13. Okay, so my first column's all set. My second column, I have a 1 in the pivot position already. I want a 0 underneath it. So my next row replacement is going to be, I need to change row 3 to be itself minus 5 row 2. Okay, so row 1 and row 2 we're not changing. I'll copy those. Okay, negative 5 row 2 plus row 3. So that stays 0. Negative 5 times 1 is negative 5 plus 5 is 0. Negative 5 times 2 is negative 10 plus 13 is 3. Okay, so if I translate this back to equations, I now have it in echelon form. I have 1 in each pivot position with zeros below it. So it's not reduced echelon form, but it's echelon form, which is enough to be able to tell if the system is consistent. So this first row says that x1 plus 5x2 is 0. My second row says x2 equals 2, and my third row says 0x1 plus 0x2 equals 3, which is equivalent to saying 0 equals 3, which is impossible. So this system is inconsistent. There is no solution, which means there is no x1 and x2. So to back up a little bit, there is no x1 and x2 that we can use as weights on 1, 2, 3 and 5, 11, 20 to create 0, 2, 13. So is 0, 2, 13 a linear combination of 1, 2, 3 and 5, 11, 20? No. We can't find any weights that will work. Is 0, 2, 13 in the span of 1, 2, 3 and 5, 11, 20? No, because the definition of span is the set of all linear combinations. So we know that 0, 2, 13 is not a linear combination of those two vectors, which means it is not in the span. Let P stand for the plane in R3 that contains the vectors 1, 2, 3 and 5, 11, 20. Is 0, 2, 13 in that plane? No, because the plane that contains those two vectors is the span of those two vectors. It's just another way of asking the same question. Is it a linear combination of those two vectors? Okay, new question. Is 2v1 plus 3v4 in the span of v1, v2, v3, v4? Yes, so the span of a set of vectors is all of the linear combinations of those vectors. And a linear combination is where you put a weight on each vector and add them together. So 2v1 plus 3v4 is definitely in the span because we can put a weight of 2 on v1, put a 2 on there. We're going to put a 0 on v2, a 0 on v3, and a 3 on v4 to build 2v1 plus 3v4. Okay, we want to draw the span of 2, 1. 2, 1 is a single vector. Span means the set of all linear combinations of the vectors in the set. And a linear combination is when you put weights on each vector and add them together. So we only have one vector, so we can ignore the add them together part. We're just going to put weights on 2, 1, different weights on 2, 1. So 2, 1 is definitely in the span, so I'm going to plot that, 2, 1. And then any multiple of 2, 1 is also in the span, so say 4, 2. Or -2, -1. 0, 0 is definitely in the span. We'll put a 0 weight on 2, 1. -4, -2. So it looks like the span of 2, 1 is this line. If I want to write this in set builder notation, I could say it's the set of all vectors that are a multiple of 2, 1. So we would do 2, 1 times A, such that A is any real number. I could also distribute the A into the vector. So I could say it's the set of all vectors that look like 2A, A. such that A is an element of the reals. Okay, so I have U and V. U is 3, 2, and V is 2, negative 1, and I want to compute U plus V, U minus 2V, and sketch the results. All right, so I'm going to sketch U and V first. So U is 3, 2, so I go over 3 up to this vector is U. And then V is 2, negative 1, which is this vector, V. U plus V is 3, 2 plus 2, negative 1, which is 5, 1. So I'll plot that one. 3, 4, 5, 1. Okay, so you should notice that U plus V corresponds to the fourth vertex of a parallelogram whose other vertices are the origin and the original two vectors. So let me just draw it out for you. So if I make a parallelogram that contains the origin, U and V, and the sum, U plus V, we get this parallelogram. Let's see if it works with U minus 2V. So U is 3, 2, and negative 2V, negative 2 times V would be negative 4, 2. All right, so I'm going to add U and negative 2V. Do this in a different color. Here's U. Negative 2V is negative 4, 2, which is right here. And if I add them together, U minus 2V, 3 plus negative 4 is negative 1, and 2 plus 2 is 4. So I get negative 1, 4 right here. It is the fourth vertex of a parallelogram containing U and negative 2V and the origin. Get a parallelogram. Is 156 in the span of 100 and 156? If so, express it as a linear combination. Okay, it definitely is, because I can write 156 as a linear combination of those two vectors. It is 0 times 100 plus 1 times 156. So 156 is definitely in the span of these two vectors. Is 156 in the set 100, 156? Yes. So you'll notice the word span doesn't appear here. The reason the answer is yes is because 156 appears right in the set. So 156 is an element of the set. Let P stand for the plane in R3 that contains the vectors 1, 2, 7 and 0, 2, 4. Is the vector 5, 8, 6 in that plane? This is just a fancy way of asking, is 5, 8, 6 a linear combination of 1, 2, 7 and 0, 2, 4? So I'm saying, are there some weights, x1 and x2, such that x1 times 1, 2, 7 plus x2 times 0, 2, 4 equals 5, 8, 6. All right, so I could make an augmented matrix and row reduce, or I could try to reason this out. So because of this 0, in order to build a 5 here, x1 has to be 5. So you would have 5 times 1 plus something times 0 to give you 5. So x1 has to be 5. So if I put a 5 here, let's see if we can figure out what x2 has to be. Okay, so 5 times 2 is 10. So this 5 times this 2 gives me 10. I need the second component to add up to 8, which means that this x2 would have to be a negative 1, so that I get negative 2 here. So x2 would have to be negative 1. x1, 5, x2, negative 1. Let's just make sure that the third component is true if I use x1 as 5 and x2 is negative 1. So we have 5 times 7 plus negative 1 times 4. That's 35 minus 4 is 31. That doesn't give me 6. So it does not look like there's a solution. Like there is not an x1 and x2 that you can put on this vector and this vector, add them together to get 5, 8, 6. And what does the span of two vectors in R3 look like geometrically? I'm going to refer you to the answers on the next page, because I just realized I am doing the even more practice / challenge problems. So see answers. It is written out there.